All right, so what you're being asked to do is using your notes from Friday, and if you weren't here Friday, I've been sending notes to everybody by email. And if you don't have email at home, you can go to the school library. You can come in here and print them out. So you have every opportunity to have all the notes every day. Okay? That doesn't excuse you from taking notes in here, because writing it down for yourself helps you learn. So, using the notes from Friday, you're supposed to first write the electron dot notation for carbon. Well, carbon has 4 valence electrons. It has 6 total electrons, but only 4 valence electrons. And we've gone through all the orbital notation and such like that to figure out what valence electrons are. So we're going to put 1 electron dot on each of the 4 sides of carbon.
Wait, how is it 4? I thought it was 2.
Okay. If we have the periodic table out here, hydrogen and helium each represent the placement on the periodic table, represent the placement of an electron in the first primary energy level. Carbon, though, is located on the periodic table in the second period. So its placement there represents the placement of electrons in the second period. So that second period, since that's its highest energy level, is the valence level. All the electrons in the second period of carbon are the valence electrons, and that includes the placement of electrons where lithium and beryllium are here in the second S sublevel. So there's 2 electrons in 2s and 2 more electrons in 2p, representing where we put boron and carbon here, because this is the p sublevel region of the periodic table. So there's 4 electrons, 1, 2, 3, 4 in carbon's valence level. Okay, so then it said number 2 was to write the electron dot notation for hydrogen 4 times. The electron dot notation for hydrogen is just 1 dot. Hydrogen on the first primary energy level, and there's only 1 electron representing where it's placed there on the periodic table. So there's only 1 dot in hydrogen. Okay, 1 electron in its valence level, only 1 electron period for hydrogen. And we need 4 of them. And you can put the hydrogen dot here, or you could put it here. Or you could put it here, or you could put it here. Nothing wrong with any one of those 4 sides. You could put them all on the same side. I just chose all 4 sides to remind you of that. Okay? I could have arranged, please don't play with the balloons yet. I could have arranged the hydrogens around the carbon if I wanted to, but it's not required. You can still get to the same result without it. Okay? So either one of these is fine. Then the next thing was to combine the carbon and hydrogen electron dot notations in a sharing arrangement. Well, a sharing arrangement is the way that we show how carbon and hydrogen will share electrons to get both the carbon and all the hydrogens to have the number of valence electrons they'd like to have. Carbon, being in the second primary energy level, would like to have 8. Hydrogen, being in the first primary energy level, or in the first period of the periodic table, would like to have just 2. So if I share this electron right here with this one, that gives carbon access to this electron, hydrogen access to this one. So hydrogen now has 2 electrons because it's going to share that orbital with those 2 electrons. And if I share this one, now that hydrogen has 2, carbon has 6 at this point. If I share this one, now this hydrogen has 2 and carbon has 7. And finally, if I share this one around here, now carbon has the 8 it would like to have, hence the octet rule. And each of the hydrogens have the 2 electrons they want, so they both have full valence levels. Okay, and if we want to personify these atoms, we'd say they were happy. Okay, we could also share them like this if you arranged your hydrogen and carbons in this manner. Both of these are perfectly okay. It gets you to the same result. Okay? What now? Well, this is the sharing arrangement. You don't do that until you get to what's called the Lewis dot formula. And that's what we're going to do next. So from this then, using your notes from Friday, you're going to write the Lewis dot formula. So we're trying to get there where you're talking about, okay? But when we get to more complex molecules in the next couple of days, it's going to be important for you to probably start with this sharing arrangement, okay? It works out a lot better when you, I mean, occasionally I'll have a student that can go straight to the Lewis dot formula, but I want you to do the sharing arrangement for me in here, okay? So write the Lewis dot formula using your notes from Friday.
What happened to the other doors in Lincoln, Texas?
Well, I took them down for the test. This is a new model. Well, I'm going to show everybody, so. Okay, yeah, good. All right, so when we put the carbon and the hydrogens together into a Lewis dot formula, if I have a carbon and hydrogen joined together, squeezed together, and that's the term I used in the notes on Friday. Squeeze all the element symbols together. If I squeeze them together side to side, that squeezes the electrons over and under. If I squeeze them over and under, that squeezes the electrons side to side. Okay, if I squeeze them over here side to side, the electrons become over and under. If I squeeze if I put the hydrogen and carbon close to each other here, it's going to squeeze the electrons side to side. Okay? Any of you who like to go hunting, this is like looking at the barrel of a double barrel shotgun. This is like looking at the barrel over an under shotgun. Okay? All right. We're in the South, so people kind of relate to that. All right. Sometimes. All right. So then number 5. Draw an electron pear shape. If you look on your notes from Friday, it should tell you how to figure out what that shape's going to be very explicitly. Okay. So then, carbon is the central atom in our arrangement here. And if we have 4 sets of electrons, a set of electrons is any number of electrons shared between 2 atoms. It might be 2, it might be 4, it might be 6. Okay, but any set of electrons is the number of electrons shared between 2 atoms. So between the carbon and each hydrogen, there's 2 electrons shared there. That makes 4 sets. Anytime you have 4 sets of electrons around that central atom, that's going to create for you a tetrahedral arrangement. Okay? And there's a tetrahedral arrangement. And since this is an electron pair shape, we're going to put those 4 sets of electrons on each of these, we could call them arms. Okay? So that's our electron pair shape for methane. Now I put the double set over on the left side, but it's perfectly okay to put the double set over on this side. Okay, nothing wrong with that. For that matter, I could put the double set at the top if I really wanted to. Makes it a little tricky to figure out sometimes, but that's okay. I could put these 2 arms here and here and put those 2 up there. Okay? So then, now we're going to replace as many pairs of electrons as are shared with the element symbol they're shared with. Let me show you how to do that. If you don't remember, if you do know how to do that, go ahead and do it. We did show you this on Friday. We did practice it on Friday. I tried to. Yep. Yeah, we'll get there eventually. Yep. Okay, so we're going to replace as many pairs of electrons as are shared in the Lewis dot formula with the element symbol with which they are shared. So here's our Lewis dot formula right up here. And here's our tetrahedral arrangement. The first thing we want to do is redraw this tetrahedral electron pair shape in pencil. Now, word of warning, a lot of students try to skip over steps or write it in pen because I can do this. But they forget we're going to get the harder stuff. So if you'll follow all the steps I'm teaching you, you'll get there with a lot more assurity. Being a lot more assured you'll have the right answer when you're done. Okay? So follow the steps. Yes. I'm listening. If you can. Yeah. This is a tetrahedral electron pair shape.
Right. So, do I need, how many things are on the sides of the triangle?
There's 2 arms. This triangle right here means it's coming out toward you.
Okay.
And there's a pair of electrons on the end of that arm. And this dotted line means that's going back behind everything. And there are 2 electrons on the end of that. Corresponding to there's 4 sets of electrons here, 4 sets of electrons here. Altogether 8 dots. Okay, so I'm redrawing this. Now, if you're doing it in pencil, this is what I'm asking you to do. Do it in pencil. Then you're going to replace element symbols. We're going to replace those pairs of electrons, those sets of electrons with element symbols for everyone that's shared up here. Well, all of them are shared up here, aren't they? Now, the one we did on Friday, there were 2 that were shared and 2 that were not. This is shared. All these are shared. Okay? So we're going to replace all 4 sets of electrons with hydrogen element symbols. As are shared in the Lewis dot formula. So all of these sets of electrons around that central carbon are shared with a hydrogen. So we're going to replace all of them in this next drawing. Either one of these drawings are fine. Okay.
You can't just have it going from 4 different ways. You have to have like a 3D looking one.
You've got to have a 3D looking one, yes. Okay, since there are no more electron pairs,
Is that number 7?
nope. Okay, since there are no more electron pairs in this last drawing, we replaced all the pairs of electrons with a element symbol here. Well, this is the molecular shape. Once you've gotten rid of the electron pairs using the step-by-step procedure I teach you, it might be 6 steps, it might be 7 steps, depending on whether there are electron pairs left over in this step. Since there are no more electron pairs, this is the molecular shape. When you reach the end, when there are no more electron pairs, that's the molecular shape. Since the name of this shape up here in the beginning was tetrahedral, this is also tetrahedral, and that makes the molecular shape tetrahedral. Okay? Now, on Friday, I showed you what that would look like when we overlapped orbitals. Remember that? We said we had a carbon here, and the carbon actually goes through hybridization. So we had one orbital that goes up, one that goes out to one side, one that comes out toward you, and one that's back behind that one. Okay? So the hybridized orbitals of carbon, these are the hybridized orbitals of carbon. When we changed we did their orbital notation, and we showed that when you combine the s and p orbitals together in such a way that you started out with 4 orbitals, 1 s and 3 p's, and when you end up, you have 4 orbitals, but these are not s and p's anymore. It's the same, all the same 4 orbitals, not different kinds of orbitals. And we call them sp3s. If we're combining and rearranging 1s and 3p's, the resulting hybridized orbitals are called sp3s. Okay? And what I showed you on Friday was that these hybridized orbitals actually overlap with the s orbital of a hydrogen atom. We did it with water, so that with an oxygen in the middle. Okay? We're overlapping with the hydrogen atom. Okay? So this was the way we showed it in Friday's notes. All right. But something else actually happens. There is an overlapping. The orbital of hydrogen and this sp3 orbital of carbon, and all these sp3 orbitals with these separate hydrogens, they actually become one combined orbital, and that combined orbital is called a covalent bond. So that one electron from the hydrogen and one electron in this sp3 orbital are combining together in the same orbital that we call a bond, a covalent bond. Okay? but there's a slight change in shape here when that happens. So these bonds, covalent bonds, are shared orbitals. When you have a covalent bond, you have a shared orbital. The kinds of bonds we're forming here that lie around a line between the atomic nuclei are actually wiener shaped. And they are called wiener bonds. No. Sigma bonds. Okay? So this shared set of orbitals here, the s orbital from hydrogen, the sp3 orbital from carbon, when they actually join together, they don't actually look like this anymore. They join together into this wiener shape. Okay? It's not a hot dog because a hot dog has a bun. There's no bun here. Okay? It's a wiener. Alright? So the carbon's right here and the hydrogen's right here. And this bond right here, or the overlapping of the orbitals, changes into the same sort of shape. Alright? We get this wiener shape. And this bond, this orange one, which is supposed to be kind of coming out toward you, if we go back to the three-dimensional molecular drawings we did, it's kind of coming out toward you here. That's what that triangle means. So I want to make this wiener sort of three-dimensional, okay? A 3D wiener. Okay, and so the hydrogen's out here. And this one back here in the back, the one we drew as a dotted line, and our 3D drawing of the molecular shape for methane. I'll make it sort of three-dimensional shape.
What is that, they're called sigma alpha? Is that what you're trying to say?
Sigma. No, that's not an alpha.
Oh, it's no.
Alpha, remember, has a tail on the bottom. This one only has a tail, a little switch on the top.
Okay.
Okay? So this is more what the shape of the bonds would actually look like. Okay? So those shared electrons in this shared set of orbitals between carbon and hydrogen are arranged or keep themselves in a sort of a wiener-shaped region between the carbon and the hydrogen. Okay? All right, so your balloon model of methane will look a lot like this, except the hydrogen atoms will be spheres, and the carbon atom won't be shown. Okay, we put the carbon atom here in our drawing, but what will happen is you won't actually see the carbon atom. And if you do it well, the resulting balloon shape will arrange itself tetrahedrally. It'll form a tetrahedral for you so you can see what happens. Now, the reason that it forms a tetrahedral is the same reason that this molecule forms a tetrahedral. Try to remember that electrons have a negative charge. Like charges repel. Charges that are the same tend to repel each other, except we can get two electrons in the same region if they have opposite spins. Opposite spins cancel the electromagnetic repulsion. Like charges tend to fly apart, but if I have opposite spins, they can get together because the opposite spin cancels that electromagnetic repulsion. Electrons that spin in one direction cancel out the spin from an electron spinning in the other direction. That's why we do orbital notation with an upspin and a downspin. The upspin means you got an electron spinning in one direction, and this is an electron spinning in the other direction. That cancels the electromagnetic repulsion. Opposite spin cancels out what would otherwise make like particles repel. Like charged particles repel. Okay? All right. Opposite spins of electrons cancel out the electromagnetic repulsion that would normally make particles with the same charge fly apart. Well, they can be together. They won't go like crashing into each other, but they can be in the same region. Okay? It's like the north and south pole of a magnet are attracted to each other, but the north and north pole of two magnets fly apart. Okay? If we can cancel the electromagnetic repulsion, you can get the north and south, you can get north and north pole together, but you can't do that with a magnet. Okay? You know, I don't know the answer to that question. That's a good question. All right, now, so before we do our molecule of methane, I want to do a model of just the hybridized orbitals of carbon. Okay? I want to do the sp3 hybrid orbitals of carbon. All right, now we're doing the sp3 hybridized orbitals of carbon, but it could be any atom that hybridizes. Any atom that hybridizes would form the same sort of arrangement, okay? And if you recall, we're just making this part right here. So we have one balloon going up, one balloon going out to the side, one balloon coming out toward you, and one's behind, yes. All right? So you're going to need 4 balloons, all of different colors. 4 balloons, all of different colors. Huh? Round ones, yeah.
You just had to bring long ones.
No, I said both round and long.
Oh.
I'm sure. Both round and long balloons.
When did you tell us that?
It's right over there.
It was earlier. I got balloons with the tiny. Those was on the No, I don't know. My house
All right, so you're going to need 4 balloons. And you need to blow them all up the same size. Not long balloons, round balloons.